All right, this is Honors Algebra 2 Pre-Calculus. We're doing 4.3 in Pre-Calc, which is right triangle trigonometry. So in this video, we'll find the values of the 6 trigonometric functions in right triangles. Trigonometric functions relate the sides of a right triangle, the adjacent, opposite, and the hypotenuse, to the oblique or non-right angles in the triangle. In general, you'll be given a triangle with one side missing, and you'll need to use Pythagorean theorem to find the other missing side. So just a reminder of SOHCAHTOA, which we've gone over in other videos, so I won't go into it, but you can certainly take a look. You want to make sure you memorize these relationships. All right, so we're going to find the exact value of all the trig functions of theta, right? So we are missing a side here. So you can either use Pythagorean theorem, right? Or you can recognize that this is a Pythagorean triple. So let's do a quick Pythagorean triple thing, right? So the Pythagorean triples. There are lots of them, but the ones that come up all the time, and remember they go leg, leg, hypotenuse, right? So 3, 4, 5, or any multiple of 3, 4, 5, right? So 6, 8, 10 is a 3, 4, 5 triple, right? 5, 12, 13, right? 7, 24, 25. 8, 15, 17, and 9, 40, and 41. Right? So those are the ones that are worth memorizing. So I would suggest now there are more than that. And years ago, one of my students actually came up with an interesting way to see if we could figure out if there was a pattern for the Pythagorean triples, and there actually is. It's kind of cool. Again, this is just a cool side note because I'm bad at staying on task even in video lessons, right? So cool side note, years ago, one of my students named Will was like, hey, Hogan, I think I figured out a way to make Pythagorean triples. And so we kind of like walked through it and figured out if it's true. And sure enough, if you take the smallest number, right, so if you take whatever the small leg is, right, and you square it, if that small number is odd, if you take the square and split it into essentially halves, you'll get the other two, the leg and the hypotenuse. So here's what I mean by that. 9 squared is 81. If you were to split 81 into halves, you can't split it into two equal halves that are whole numbers, right? So you would split it into the two numbers in the middle that are the closest to the halves, which would be 40 and 41, right? And sure enough, 9 and 40 and 41. And if you test that with 7, it also works, right? 7 squared is a 49. Well, if you were to cut 49 in half, the two numbers you'd get that are closest to cutting it in half are 24 and 25. Same thing with a 5 squared, right? 5 squared is a 25. Well, sure enough, if you split 25 into the two closest to halves that you can get as whole numbers, you'd get 12 and 13, and the same thing works with 3. It does not work with even numbers. The pattern with even numbers is the same idea, except essentially what happens is you have to cut the square in half. So if you notice, 8 squared is 64. I'm not using 64. I'm using half of the 64, which is 32. And then I can split 32 into these two numbers, the 15 and the 17. I realize that 32 actually does split into 16 and 16, but that's the pattern. You can actually, so I did a proof once because when Will brought it up, I thought, boy, we should figure that out. And so we made a supposition. We started with the odd numbered example, and we basically suggested that if this is 2n plus 1, right, if this is an odd number, then essentially what happens is if you did 2n plus 1 squared, right, and so if you squared it, and subtracted 1 and divided by 2. So if you did 2n plus 1 squared, that would be an 81, right? Minus 1 over 2, there's your 40, right? And if you did, so that's the next one, right? So like leg. And then the hypotenuse would be what happens if you did 2n plus 1 quantity squared plus 1, which would mean an 82 divided by 2. And it totally holds up. It's pretty cool. And you can do a proof to figure it out. I'm not saying it's worth it, and I probably shouldn't have bothered with this cool side note, but I did, so here we are. So all of that to say that this number, you could either use Pythagorean theorem or you could use your memory to realize that this number is a 40. Once you have it's a 40, it's a pretty straightforward problem. So once you know that this is a 40, it's all about just knowing what SOHCAHTOA is, right? So the sine of theta is the opposite, which in this case is 9. Remember, opposite and adjacent are relative to the angle. Opposite means not touching the angle. Hypotenuse doesn't change. The hypotenuse is always the one that's opposite the right angle. So opposite, 9 over hypotenuse, 41. Cosine will be the adjacent, 40 over 41. And tangent will be the opposite, which is 9, over the adjacent, which is 40. So SOHCAHTOA. And then again, once you know those three, it's pretty easy to just flip them and find the other three, which is why I suggest writing them in this order. So I get 41 over 9, 41 over 40, and 40 over 9. And that's it. So again, diversion about the Pythagorean triple. So again, if you've memorized your Pythagorean triples, you know what this missing side is. If you don't, so back here, if you didn't know what this side was, right, you could have said, hey, the missing side squared plus 9 squared gives me a 41 squared, but you can see that that's not something you're super stoked about doing in a calculator, right? Like, I'm just guessing off the top of my head that that's not a thing you're really stoked about. It ends up being x squared plus 81 equals 400, nope, not 400, 16, my bad, 1681. So 1681. And then you subtract the 81 and you get x squared is 1600, which is how you get x is 40. But again, not super duper fun times, right? So same thing here. If you don't know what this side is, like, it's great if you remember that there is a Pythagorean triple that is 5, 12, 13, right? That's awesome, because if you do that, you can say, oh, there's the hypotenuse that's 13 and there's the leg that's 5. If you don't see that, you would have to do 5 squared plus x squared equals 13 squared. You get x squared is 169 minus 25, which is how you get x squared is a $144, and then we get to 12, right? The side length can't be negative when it's just a random triangle floating in space. When we start to talk about triangles being in a position on the coordinate axes, then we can start to talk about a negative side because it can indicate a direction. But when you just have a triangle randomly floating in space, you don't have a negative side. Okay, so, sorry, we're beach balling for a sec. Okay, so once I know that side, again, it's a pretty straightforward task, right? So my sine is the side that's opposite, which is the side not touching the theta. So opposite over the hypotenuse, which is the side that's opposite the right angle, right? The hypotenuse doesn't change. The hypotenuse will also be the longest of those three sides because it's opposite the largest angle. So the cosine will be 12 over 13. The tangent will be 5 over 12. And then for my other three trig functions, I just flip those, right? So cosecant is 13 over 5. Secant is 13 over 12. And my cotangent is 12 over 5. And that's it. All right, so we're going to sketch a right triangle corresponding to the given situation, right? And then we're going to use Pythagorean theorem to find the third side and then find the other trig functions. So remember that secant, right? So secant is the flipped version of cosine. So secant, which is 6 over 1 here, because everybody's secretly a fraction, is instead of being, so cosine is adjacent over hypotenuse, so this is going to be hypotenuse over adjacent. So I'm going to go ahead and sketch a version of this triangle, right? So here's my theta. It does not have to be pretty. I know that the adjacent side is a 1. I know the hypotenuse is a 6. So I'm going to find this missing side, right? I'll call it y because it's up and down, right? So I'm going to say 1 squared plus y squared equals 6 squared. So y squared seems to be 36 minus 1. Y seems to be the square root of 35, which is about as nice as it gets because 35 doesn't have any perfect square factors or anything else. So now I can find all of the trig functions. The sine is opposite, right? And again, opposite means the side not touching the theta. For right now, the opposite side has always been on that side because theta has always been in this bottom angle. But it doesn't have to be. Theta could have been this angle up here if I'd drawn the triangle differently. So just be aware of that. So opposite over hypotenuse, right? My cosine is going to be adjacent over hypotenuse, which makes sense because I already had the secant as being a 6. And my tangent is going to be opposite over adjacent, which you could just write as a root 35. So now when I flip them, right, my cosecant is going to need to be simplified a little. It's a 6 over a root 35. So when I rationalize by timesing by a root 35 over root 35, I get 6 root 35 all over a 35, right? My secant, I already knew it's a 6, right? But that was actually given, right? That was the information I was given in the first place. And then my tangent, sorry, not tangent, cotangent, my bad. My cotangent should be 1 over the tangent, so 1 over root 35. When you rationalize that, you get root 35 over 35. And it's okay to skip to that if you can rationalize things in your head. All right. Go ahead and give this a try. You're going to draw a triangle that has a cosine of 5 over 7, right? So cosine theta is 5 over 7. And then we'll go ahead and walk through the same steps. So draw a triangle. It doesn't have to be drawn to scale. Nobody cares. So there's my theta. Again, I put it at the bottom. You don't have to. You could have put theta at the top, right? So I know that cosine, because SOHCAHTOA, I know that cosine is adjacent over hypotenuse, right? That's the CAH, C-A-H. So my adjacent is 5, my hypotenuse is 7, so I just have to find this missing side, right? So 5 squared plus y squared is 7 squared. Y squared seems to be a 49 minus a 25, which is a 24. So my y seems to be the square root of 24, which you could leave it as the square root of 24. It does also have a 6 times 4, so I could pull out the 4 and make it a 2 root 6. So my sine, right, is going to be this y value, this 2 root 6, opposite, over hypotenuse. And remember, opposite is the side not touching the theta, right? Because it's opposite theta, right? And that's it, right? My cosine was already given to me, but I should check anyway. It should be 5 over 7. That was given. And my tangent should be the 2 root 6 all over a 5. So those are my first three, and then I just flip them, right? So my cosecant is going to be a 7 on top of a 2 root 6. I'm going to multiply by root 6 over root 6, so I'm going to get 7 root 6 all over 12, right? My secant is going to be a 7 over 5, and my cotangent, I'm going to get this, so it's going to be a 5, my bad. My cotangent is going to be a 5 over the 2 root 6. When I multiply by root 6 over root 6, I get 5 root 6 all over a 12. Now, if you had left this as a root 24, your answer should be slightly different, but it would be the same basic idea, and it would be fine depending, if it's multiple choice, it would be an issue that you hadn't simplified to match the answer. But, all right. So, example 3, find the values of theta in degrees from 0 to 90 and also in radians from 0 to pi over 2. So basically we're saying in quadrant 1 without the aid of a calculator. So what they're saying is, where is the sine a half in quadrant 1? Because that's what this says and that's what this says. Well, sine is a half right here. So my answer is that theta is 30 degrees, which is the same as pi radians, right? So theta equals 30 degrees, which is the same as pi radians, right? They're all the same. It's just a different way. It's like saying inches versus centimeters. It's the same idea. It's just a different measurement. So the answer is right here, because I'm looking for where the y on the unit circle is 1/2, right? And the y on the unit circle is 1/2 at this spot, 30 degrees and pi over 6, same spot. All right. All right, you're going to do the same thing. Again, we're talking quadrant 1, right? In quadrant 1, where is the x on the unit circle? A root 2 over 2. Well, all of the root 2 over 2's happen at the 45-degree angles or the pi over 4's, right? So this is a root 2 over 2 comma root 2 over 2. So I want that theta is 45 degrees, which is the same as pi over 4, right? 45 degrees and pi over 4 radians are the same thing. All right, same idea. This one's a little bit harder. So again, we're in quadrant 1, but this time we want where tangent is root 3. Well, now this is harder because tangent is the y on the unit circle on top of the x in the unit circle, and we're seeing that is a root 3 over 1. So I can instantly rule out the pi over 4 because that would be root 2's, right? So I see the root 3 and I think, okay, this is either a pi over 3 or pi over 6. What I'm going to do is I'm going to recognize that on the unit circle, the root 3 is over a 2. So what if I multiplied both the top and bottom by a half? Couldn't I make this look like the stuff on the unit circle? And I'm pretty sure I would get a root 3 on top of a 1/2. And so I say to myself, oh, I want where the x is a 1/2 and the y is a root 3 over 2. That's up here. So the reason I multiplied by the 1/2 over 1/2 is so it looks like the unit circle. Right? Now, as you get better at this, you don't necessarily have to do that, right? But that's kind of the idea. So I say, cool, my answer is that theta is 60 degrees, which is the same as pi over 3. All right, you're going to give that a try, right? You're going to do same thing, except it's going to be that same quadrant 1, but you're looking for where tangent of theta is a 1. So remember, tangent is the y on the unit circle on top of the x on the unit circle, and you're looking for where that's a 1. Well, that's the same as if you multiply the x and the unit circle over, that's just saying where are they the same value? Well, the only spots on the unit circle where the x and y have the same coordinates at each point are the root 2 over 2's, right? And they might have different signs in different quadrants, but the only one where they have the same value is here. So my answer is going to be 45 degrees or pi over 4 because they're the same thing, right? All right. So now it's getting a little bit trickier, right? So I would argue that if you use a little bit of logic, so again, we're still in quadrant 1, I would argue if you use a little bit of logic, you can figure this one out. You're looking on the unit circle, because they said without a calculator, so that means it's got to be on the unit circle, for where the y on the unit circle, sorry, I didn't mean the y on the unit circle, I meant 1 over the y. Come on, brain. You're looking for where 1 over the y on the unit circle is a 2 root 3 over 3. So here's the thing. There's a mental leap here, which is that the y on the unit circle involves a root 3, right? Because I know that it's on the unit circle. They said without the aid of a calculator. So I say, you know what? It's got to be where the y on the unit circle involves a root 3. Yo, that's this one, right? That's the 60 degree or the pi over 3, because that's a 1/2 and a √3/2. So you could probably mental leap it and be like, that's a little bit of a cheat, but I'm going to go ahead and say 60 degrees or pi/3. I'm still going to walk you through how you could logic through that, or like how you can work through it correctly, but it's also not like horrible cheating to make a mental leap like that, right? It's sometimes we make mental leaps based on prior knowledge, and that's not a bad thing, right? So if you were going to do it the official way, right? I guess. I mean, there's not really an official way, right? The job is to get to the right answer, and if you get there by using a mental leap, then cool. But if you were going to do it the official way, what I would probably do is I would probably solve this thing for y, right? I'd probably cross multiply and get that 3 equals 2 √3 times y on the unit circle. 3 over 2 √3 is the y on the unit circle, and then I would need to rationalize, right? So I'd say, cool, this 3 over 2 √3, I don't really want to keep a √3 on the bottom. So when I rationalize, I get 3 √3 over what seems to be a 6, which means that when I cancel these, I get a √3/2 is the y. And then that spits me out at the exact same spot where I'm like, oh, hey, the y on the unit circle is a √3/2. But again, if you totally were able to see that logically, that's not wrong. Okay, so we want to know where the secant is √2. Again, I'm going to argue that there's a strong possibility for a mental leap here. So I am in quadrant 1, right? But this is saying where is the 1 over the x on the unit circle equal to a √2? So it's not wrong if your brain makes a leap and says, it's an x with some √2. Well, the only points on the unit circle that have √2s at all are the 45 degree angles, right? The pi/4s. So if you were able to leap from this and say, cool, so that means that theta is 45 degrees or pi/4, that's not wrong, right? I mean, that's what's going on. That's what's going to happen. You know it's a value on the unit circle because they say without the aid of a calculator. Or if you had to go the other route, you could say, cool, 1 over x on the unit circle is a √2. So if I multiply this over, I'd get 1 equals √2 times the x on the unit circle. 1 over √2 is the x on the unit circle. When you rationalize, that becomes a √2/2, and boom, you land at the same spot, right? Cool. So I'm definitely not here to penalize you for making mental leaps. I think mental leaps are dope. All right, so that's it for the first video.